Okay, how's it going, everybody? So this is our first flipped lesson of the year, and so I'll talk a little bit about how this works, and then we'll go ahead and get started on it. So you're going to be seeing me complete each one of these problems that I have on my lesson, and I'll be talking my way through it as I normally would. You should, of course, be copying down what I'm writing, but not only should you be copying down what I'm writing, but you need to also write in your own words what I'm saying. What am I actually saying? The explanations I'm giving is actually more important than what I'm actually writing on the board. If you only write down what I have on the board, you're not going to remember why I did certain things. So make sure you hit pause if you need to, and rewind if you need to, if I'm going too fast, so that you can make sure that you can totally complete your notes and get everything down that you need to in order to be able to replicate these steps on future problems. Okay, so for this first problem, so where these topics came from is I had a few students, not that many, text me their comments of the topics that they wanted me to do, and so I just put them in the presentation here, and in doing so, I'll just go through them. And it's kind of disjointed, they aren't really connected all that closely, but I'm just going to make sure I cover them all. All right, so the first one was somebody wanted me to review upwards division. So the very first thing I'm going to do with upwards division is I'm going to write my problem 47 thirds, but when I do it, I make sure that I write it a little bit wider than I normally do. Actually, I'm going to make that a little bit different. I'm going to drop it down just a tad, sorry. 47 thirds. Okay, so then now I'm basically going to do the exact same algorithm that we're used to doing with our traditional division, and that is I'm going to check and see how many times 3 goes into 4. How many times 3 goes into 4, and I know that 3 goes into 4 one time, and then I multiply. So I'm going to multiply 1 times 3, and that gives me 3, so then I subtract 4 minus 3. And 4 minus 3 equals 1. I take this 1 right here and I bring it down here. So now I have the number 17. And then I say 3 goes into 17, and I know that 3 goes into 17 5 times. And then of course I do 5 times 3, and that is 15, so I subtract 15, which equals 2. And the very last step, and the major benefit of doing upwards division, is the fact that it helps you write your fraction. And so my fraction is going to be this 2, which is already located as a numerator. It's already here on the top, is going to become my numerator. And the 3, which is the only denominator that I've had, is going to be my denominator. So then my final answer is 15 and 2/3. Okay, so now I'll do the same thing for this one. I'm going to rewrite it so that I have a little bit more space in between my numbers. And then I say, okay, how many times does 8 go into 3? Well, that's 0. How many times does 8 go into 35? And 8 goes into 35 4 times. And 4 times 8 is 32. So 35 minus 32 gives me 3. So this number is 32. So then 8 goes into 32 evenly. So that's going to be 4 times. 4 times 8 is 32. With a 0 remainder there, so that's a 0 in front. And then 8 goes into 7 0 times. 0 times 8 is 0. Oops, that's a 0. So then that gives me a remainder of 7. So my final answer is 440 and 7/8. The nice thing about, or the main benefits of the upwards division is you know where this remainder is supposed to go. It goes in my numerator. and you know where this denominator is supposed to go, it goes on my denominator. Everything else is pretty much the same of the traditional algorithm. Okay, let's take a look at the next slide. Okay, the next concepts people wanted was the GCF and LCM. So I wasn't sure if that included factoring and using and getting down to the prime factorization. So I decided that I'll show that one time, and then after that I won't show it again. But I'm going to go ahead and do it the two ways we've talked about. So the first way I'll do is the factor tree. So the two factors of 36 that I can think of are 9 and 4. And remember that when you're doing factor trees, it doesn't have to be prime numbers. It could be any number that you want. So then I go the factors of 3, any number that's a factor of the 36, that is. 3 times 3, and over here I go 2 times 2. So the factors of 36 are 2 squared times 3 squared. And it's good to put this smaller number first. It's not a requirement, but it's good to do the smaller number first. Okay, now I'm going to do, on this one, I'm going to do upside down division. So on the outside of this, I'm going to only use prime numbers. The major difference between the factor tree and this is here you can use any factors you want. They don't need to be prime numbers. Here, this side number always has to be prime. So I can't use 4 right here because 4 is not a prime number. That's probably the biggest mistake that I see students make. So I'm going to use 2, and then so 2 goes into 40 20 times. And then I'm going to do that again, and I can use 2 again because 2 goes into 20 10 times. And then I can do it again, and I use 2 again. 2 goes into 10 5 times, and now I see that all of these numbers are prime. So then I have 36, excuse me, I don't have 36. I have 40 as my number, and the prime factorization is 2 to the third times 5. Okay, so now to find the GCF and the LCM. If we remember what GCF means, greatest common factor. Factors are small, which means I'm only looking for the factors that are the same in both 36 and 40. So I'm looking for the least amount or the smallest amount of factors for these two, or the factors that are the same. So if I look at this and I see, okay, I've got a factor of 2 and a factor of 2. Those are the two factors that are in common. And then I'm going to use the smallest exponent, not the largest one. So I use the smallest exponent. So for my GCF, I'm going to use the factors that are the same. So I have factors of 2 that are the same, and then I use the smallest exponent between those two. So for this one, it's going to be 2 squared, and we can leave it like that. You don't need to multiply it out. Now, I didn't do anything else because this 3 is not down here. There's no 3 in the bottom. The 5 is not a factor of 36, so I didn't have to use the 3 or the 5. So for my GCF, the answer is just going to be 2 squared. Now, for the LCM, that's different. Multiples are big numbers. Multiples are big numbers. They're giant numbers. They're going to be at least as big as either the one of these and most likely bigger. So when I do this, I don't care about common factors. It doesn't say common factors. This one said common factors. This one says common multiples. So I don't care about common factors. Instead, I'm going to use every factor that I see. So I see that I have a factor that is a 2. I see that I have a factor that is a 3. And I see that I have a factor that is a 5. Now, I go back in and I'm going to use the biggest exponent. For the multiple, because I need a big number, I'm looking at this exponent and I'm going to use the greatest exponent there is. So between the 2 squared and the 2 to the third, I'm going to use the 2 to the third. And for this one, the 3 squared, even though I don't have a 3 down here, I don't care, I'm still using that base of 3, so then I'm going to use that exponent as well. So there's the answer. The least common multiple is 2 to the third times 3 squared times 5, and whatever you multiply that out, that would give you. But this would be a perfectly legitimate answer. I don't expect you guys to multiply them out. I want to just see the prime factorization for each one of those. Okay, let's go to the next slide. So here, I've kind of cut it down for us a little bit, and I've done the factoring for us. So we already have it in prime factorization form. We're just going to find the GCF and the LCM, cut down a few of the steps there. So for the GCF, so I'm looking for the greatest common factors. So I'm looking for factors that are common. So I see you have a 2 and a 2. Therefore, I can use 2. I see that I have a 3 and a 3. So I'm going to use a factor of 3. I see that I have a 5 and a 5. So I can use a common factor of 5 as well. So for this one, I used all of the factors that are in common to both. I have 2's here. I have 3's here. And then I have 5's here. Now, I have to use the greatest common factor, so the biggest common factor. So that means I'm actually looking for the factor that fits inside the other one. So this is 2 to the third, this is 2 to the first. Well, the only thing that's common to both of these is this 2 to the first. Inside of this 2 to the third is also a 2 to the first, so I'm going to use my 2 to the first. For this 3 squared, or excuse me, for this 3 here, it has 3 to the first, that has 3 to the fourth, so I'm going to use the 3 to the first because this is in common with that one, it's included in that one. So I'm going to go ahead and emphasize this, that's 2 to the first, and that's 3 to the first. Now I look at my 5. Inside my 5, I have a 5 squared and a 5 to the fourth. Well, both of these squares are fitting inside of that 5 to the fourth, so then it would be 5 squared like that. So that's the GCF right there. Now for the LCM, what I'm going to do here is I'm going to use every single factor. Doesn't matter if they're in common or not because I need all of the factors. I'm looking for a multiple. So that means I'm going to use 2 times 3 times 5 times 7 times 13. Notice that all of those are prime numbers, and because I did the prime factorization before we started the video. So I use 2, 3, 5, 7, 2, 3, 5, don't have a 7, and 13. So I use every factor. Now I'm going to go in, and because I'm looking for multiples, which are big numbers, I'm going to use the biggest exponent. Where here I use the smallest exponent, here for the LCM I'm going to use the biggest exponent. So I'm going to use 2 to the third power. I'm going to use 3 to the fourth because that's to the fourth, that's to the first. Here we have 5 squared and 5 to the fourth, so I'm going to use 5 to the fourth. So 5 to the fourth, 7 and 13 don't have exponents, so there you go. So then this is my least common multiple right there. Multiply that out, that's what it'd give you. All right, we're going to do one more here. And so for the GCF, I'm looking for factors that are in common. And what I see is I only see one factor in common, just the 5. There's no 3, there's no 7, there's no 11, just a 5. So that means my factor that's in common is a 5. And now I'm looking for the factors that are in common to both. Well, this is 5 to the first. So that has a 5 to the first in it, which means 5 to the first. That's it. So then this is my answer. Now for my LCM. So I'm going to use all of my common factor, all of my factors, common or not. So I'm going to use 3, 5, 7, and 11. So I have 3, and now I'm going to use the biggest factor of each one. So I have 3 to the 4th, 5 squared, 7 and 11 don't have exponents, so that's it. So there you go. That is my common factor. Just like that. Okay, so the next topic that somebody wanted me to go over was integers and to do some showing using problems. So here what I'm asking you to do is I want you to show me -3 by using 7 tiles. So show -3 using 7 tiles. So what I'm going to do is I start with what's given first. So that's 1, 2, 3 negatives. Now it tells me to use 7 tiles total. What I've done so far is 1, 2, 3, so that means I need to use 4, 5, 6, 7 tiles. So I need a few more tiles there, but I don't want to change the value of -3, so I'm going to add some 0 pairs. That's 0. And that is 0. So what I have here is this here is equal to 0, and that's 4 tiles. 1, 2, 3, 4, and then 5, 6, 7. So I used all my 7 tiles. I still have -3 as my answer, and then I have a 0 pair there of 2. So I'm going to do the same thing here, or a similar thing here. This time it tells me to show 4. So I start with 4, 1, 2, 3, 4. I always want to keep my 4, but now they tell me to use 6 tiles total, which means I need to add 2 more tiles here. I add them a 0 pair, so there's 1, and there's 2. This equals 0, and so that is showing 4 using 6 tiles. Okay, let's take a look at the next slide. Alright, so now I was asked to do some multiplication problems with integers. So the first thing I'm going to do is I'm going to write down how it's best to say each one of these problems. So when I look at this first problem, the best way to say this problem is this is 5 groups of 2 negatives versus saying 5 groups of -2. When we say 5 groups of 2 negatives, that makes me think of the tiles because they're negative tiles. So it'd be 5 groups of 2 negative tiles if we complete that sentence. So that's the best way to say it. This one would be 3 groups of 1 positive. 3 groups of 1 positive tile. Okay, so those 2 aren't too bad. It's the last 2 that give us some difficulty and some trouble. So this symbol right here, as we remember way back from our early days in school, the very first time we saw this symbol, our teachers told it was take away. Now I agree that this makes it look like a negative because it's connected, but we want to think of this in terms of takeaway. So this says that I'm going to take away 2 groups of 4 positives. Okay, so you take away 2 groups of 4 positives, and then the last one here is it's take away, again, because that first number is negative, take away 3 groups of 5 negatives, which is slightly different, again, than saying of -5. I like of 5 negatives better. Okay, so the first thing we have to do is we have to be able to say them or state them correctly that will reinforce using those integer tiles. Now let's take a look at doing the problems. So here's the same exact 4 problems, so now I'm going to do them. Alright, so the first thing that this one tells me to do is it tells me to draw 5 groups. So I've got 1, 2, 3, 4, 5. There's my 5 groups. And then what's inside the group is inside this number here. This is what's inside each group. So what's inside there is 1, 2 negatives, 2 negatives, 2 negatives, 2 negatives, 2 negatives, for a total of 10 negatives. So that equals negative 10. Okay, the next one says to draw 3 groups. So there's 1, 2, 3. And what goes inside that group is 1, 2, 3. 1 positive in each side of them. So 3 times 1, of course, is equal to 3. Okay. Now, the next one is the one that's tricky because it says this right here, if we remember back from the previous slide, take away 2 groups. Well, I don't have anything to take away from it. It's completely blank. So anytime I see that I have a takeaway problem, I got to do something over here so that I can take it away. And that thing that we are going to do that we've been working on quite a bit recently is called a zero bank. So I'm going to make a zero bank of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 positives. To make this a zero bank, I need to put in my negatives. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice right here, I'm going to take a teaching moment for you guys. I lined them up. Right? I made sure that this negative is lined up with that positive. This negative is lined up with that positive. These should be in pairs, just like I did right there. Okay, now I can do some business here. This tells me right here to take away 2 groups. So just like here, where a circle created a group, a circle created the groups here. When I'm doing this problem, a circle is still going to create these groups. I'm going to be taking them away. Now, what am I taking away? I'm taking away positive 4, or 4 positives, which means I need to be circling positive tiles here so I then can take them away. So I'm going to circle 1, 2, 3, 4 positives right there and draw an arrow showing I'm taking it away. And then I'm going to circle 1, 2, 3, 4, and I'm going to take that away. And this over here is still a zero bank because those did not get taken away. So those are still zero bank. And what I have left outside of all of these circles that I have, all these green circles, what I have left is 1, 2, 3, 4, 5, 6, 7, 8 negatives. So I have negative 8. Okay, so I'm going to do the same exact thing for the last problem there. Again, I don't have what I need, therefore I need to do a zero bank, and this is a little bit bigger problem, so I have to do at least a zero bank of 15, but I'll do bigger than that. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So I did 17 integers there. It's fine. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. Okay, now this symbol here tells me to take away. So I'm going to take away 3 groups. And what's going to be inside my groups is 5 negatives. So I'm going to be circling negatives this time. So I have 1, 2, 3, 4, and 5. There's one of my groups that I'm taking away. I have 1, 2, 3, 4, and 5. There's another one that I'm taking away. And I have 1, 2, 3, 4, and 5. For the third one that I'm taking away, these right here are still a zero bank because they did not get taken away. They're still canceling each other out. And what I'm left with then is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And those are all positives, so it's positive 15. And that's how you show multiplying integers using tiles. All right, let's take a look at the next one. Okay, so somebody else wanted me to just go over the rules for multiplication and division. So I only have two rules. My two rules are right here, basically like this. So when the signs are the same, the answer is positive. Always. So I'll do a couple of examples here. Negative 5 times negative 10. Okay, these two signs are the same, so that means it's going to be a positive answer. In this case, it would be 50. I'll do a division problem here. Negative 9 divided by negative 3. These two signs are the same, which means my answer is going to be positive, which makes it equal to 3. Okay, so that's it. That's one of my rules. Signs are the same, the answer is positive. If the signs are different, then the answer is shockingly negative. Okay, the answer is negative. So an example of that would be negative 8 divided by 2. These signs are different. The top number is a negative, the bottom number is a positive, therefore it's going to be negative 4. If I had 6 divided by negative 3, signs are different, so that's going to be a negative 2. So what I'll do here is I'll do this. So a negative, when the signs are the same, that equals a positive. Or if it's like this, this also equals a positive. Oh, what am I doing? That's supposed to be in the top up there. Dummy. So let me just do this. So this all right here should be right up in that section right there. I'm sorry, I put that in the wrong section. Shoot, sorry about that. And then down below would be 1 positive, 1 negative is equal to a negative. So sorry for that little confusion there. Okay, so now let's take a couple examples here. So when I look at this one, I see that I have a positive times a negative. That's going to be equal to a negative, and then I just say 10 times 5 is 150. Okay, so then on this one I have, so that's the signs are different. Here I have negative times a negative. Here the signs are the same, so that means it's going to be positive, and 7 times 2 is 140. I don't need to put the positive sign in there. We know it's positive, but you can if you want to. And then the last one that I did here, I did a division problem. Here I have a negative divided by a negative. Those signs are the same, which means your answer is going to be positive, and it's going to be positive 6. So there you go. That's the rules for division and multiplication of integers. Two rules. Signs are the same, the answer is positive. Signs are different, the answer is negative. Okay, the next one is people wanted a little bit of help on the subtracting integers, and so I'm going to go ahead and draw them using the integer tiles, because the top numbers here are all smaller than 10, so that means if you're asked to solve these ones, you should draw the integers out and do physically what it's asking you to do. The bottom ones are bigger than 10, and so you don't have to draw out 25 negatives. We're going to use that diagram shortcut that I showed you guys, but only after we have understood and can do this. Okay, so then for this problem, for the top one, I'm not going to do anything. I'm not going to change anything. I'm going to do exactly the way it says. So what they ask me to do first is to do 5 negatives. So I have 1, 2, 3, 4, 5. Now, it wants me to, this symbol here is take away. And what they want me to take away is 7 positives. I don't have any positives to take away. So that means I have to do a zero bank. So that's 1, 2, 3, 4, 5, 6, 7. And then down below here is 1, 2, 3, 4, 5, 6, 7. And so what they're asking me to do then is to take away 7 positives. So that's taking away these 7 right here. Those go away. And what I'm left with is negative 12 negatives, or negative 12. Okay, this one will be a little bit easier to do because it's smaller numbers. So this tells me to start off with 3 positives. So I have 1, 2, 3. Then it tells me to take away 5. Well, I don't have 5 to take away, therefore I have to do a zero bank. So 1, 2, 3, 4, and 5. 1, 2, 3. Whoops. Erase that. Oh boy, sorry. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Okay, so now what it tells me to do is to take away 5 positives. So I'm going to take away my first 3 positives that I had plus 2 more. So I take those away. And then I notice over here that I still have that right there still makes a zero bank. So what I'm left with then, if I have 3 and I take away 5 positives, I'm left with 2 negatives, or my answer is negative 2. Okay. All right, and the last one here, I'm going to start with my 4 negatives. 1, 2, 3, 4. And then this tells me to take away 2 negatives. Well, this time I have everything I need. I don't need to do a zero bank because I have 4 negatives and it tells me to take away 2 negatives. So there's no reason to do a zero bank. So I'm just going to take away those 2 negatives right there. They're gone, and I'm left then with 2 negatives. And I am sorry for making these blue and not red. What am I doing? Sorry about that. So the answer then is negative 2. Okay, so that's how you show it if you have numbers that are smaller than 10. You draw them out, do a zero bank when needed. If you don't need a zero bank, like on this one over here, please do not do a zero bank. Show better understanding of knowing when you need to do a zero bank and when you don't need to do a zero bank. If a zero bank is not required, don't do a zero bank. This one was required, this one was required, this one did not. There should not be a zero bank on that problem because I have what I need. I have negative 4 and I need to take away 2 negatives. I have that, so I can take them away. Okay, now to do the shortcut, the diagram that we talked about, there's one thing you have to do, and that is that diagram only works for addition problems with integers. It doesn't work for subtraction problems. And if we notice on this, all of these are subtraction problems. So the very first thing we have to do is I have to change this problem into an addition problem. And that's when we do that keep, change, change. Or one thing that I used to say a lot was I'd say boom, boom. So I'm going to go boom, change that to a positive, boom, change that to a negative. It's always two changes. I always change 2 signs. So boom, boom, change the subtraction sign to an addition sign and the second number to the opposite sign. In this case, it's a negative 10. So then I'm going to, now I can go ahead and draw my diagram. So for my diagram, I'm looking at which pile would have more tiles in it. Would I have more tiles in the first pile or more tiles in the second pile? Well, since this has 25 and this has 10, I'm going to have more piles in my first pile. So then for that one, it gets 2 negatives. The other pile gets 1 negative. And then what I do always is circle one of each, just like that, and this tells me to add. The signs are the same inside my circle, so that means I'm adding. So I add 10 plus 25, which gives me 35. And then I know what my sign's going to be because it's whatever's on the outside is my sign, so it's negative 35, and that's my answer. Okay, so we look at this next one here. I'm going to do the same thing I did before, which is keep, change, change, or boom, boom, just like that. And now I'm going to draw my diagram, so I'm looking which pile would be bigger of tiles. I have 17 tiles here and 30 tiles here, so this one is bigger. So that's going to get 2 positives, because this is now positive 30. It was negative 30, but now it's positive 30. And then this gets 1 negative. So then I circle one of each like that, and this says to subtract. The signs are different, therefore we subtract. So 30 minus 17 gives me 13, and then because this is a positive out here, then that means it stays positive and not turned to negative. So it's positive 13. And then my last one here, I'm going to do the exact same thing I've been doing, which is all subtraction problems, I do the same. Keep, change, change. So I'm always going to change 2 signs, so that's boom, boom, like that. So that 65 is now negative 65. So my next step is to figure out which one gets 2. And if I look at it, if this pile has 40 in it and this pile has 65 in it, there's going to be more here. So then this one gets 2 negatives and this one gets 1 positive. So then what I do is I circle one of each like this. That tells me to subtract. Signs are different, so I subtract. 65 minus 40 gives me 15, and then the symbol on the outside is my symbol, so it's negative 15 for my answer. Okay, so that is how you subtract using the diagram, and it's how you show subtraction using the tiles. Okay, and the last thing that somebody asked me to do is the divisibility rules. And what I mentioned to you on the divisibility rules is that the divisibility rules can be found in your textbook. You need to just write them in your own words, read it, write it in your own words, and then come up with numbers that fit that. If you still are struggling with the divisibility rules, then please make sure you ask me on Tuesday. But I do not want to take up our lecture time going over those rules when they're literally just in a book somewhere. So if you're hoping I was going to tell you what the divisibility rules, sorry, I'm not going to. But I will help explain them on Tuesday if there's one that you don't understand. They're in your textbook. They're all over the internet. You can find the divisibility rules. I will tell you the numbers that I require. The numbers you need to find divisibility for are 2, 3, 4, 5, 6, 8, 9, and 10. The only one that we are missing here is 7. So 2, 3, 4, 5, 6, 8, 9, and 10. And they're in your book, and we can talk about it on Tuesday. Okay, that's it. I will be posting some review problems for you to look at this weekend, and then on Tuesday we will get together for your review for your test on Thursday. Have a great weekend. I'll see y'all on Tuesday.